Okay, so I'm going to be going over the idea of a self-balancing tree. Self-balanced tree. Okay. Yeah, so what is a balanced tree? So the idea here is, in order to optimize this binary searching, it really helps to have things kind of evenly split. And that's the idea of balancing your trees. A tree is balanced if the left subtree height and the right subtree height differ by at most 1. So for example, here, this complete binary tree is balanced because the height here on the right, in this case it's just it's like 1 2 3, and this is 1 2. I'm looking at the edges of the connecting the nodes, so this is actually okay. This is a balanced tree, and if you look, and you have to look at each step too. So this node is also balanced because it goes 1 2 and this is 1. So you can look at each step. Every node that follows this, you visit every node, making sure that that first rule is followed. And the height of a node is the distance between itself and the edge, the furthest child from itself. This is also something called an AVL tree, the first self-balancing tree that was ever invented, standing for its two inventors, Adelson, Yvelsky, and Landis. 2 people. Okay. It's a self-balancing algorithm that uses this idea of rotating. And one thing I'm definitely going to need is my node, so let's just make that real quick. Constructor, I'm going to have a val. I don't think I need a position like I did for the min heap. I don't think so, so I'm not going to implement that, but it might be interesting just to think maybe that would be helpful. And then this dot left, and this dot right. Okay, and because I am OCD, there we go. All right, so I have my notes. I also like the idea of having some tests set up. So let me make I'm gonna call this the AVL tree. Is that AVL tree? Okay. Constructor, nothing. This dot root equals null. Yeah, do I need to know the length? I don't know. I just love this idea of having ready access to the amount of the set of data. Like it should be something I had just quick access to. And ever since I saw this implementation, I just love it. Should I call it length or? Yeah, I'll call it length. Whatever. Length is 0. And what I'll do here is I'll have my AVL equals a new AVL tree. I don't need anything, and I assume I'll have to like add, so I'm gonna call it insert. Don't want to remove, I guess, is a thing. And rebalance, I guess, is something I'll have to consider. So let's do AVL dot root equals new node for 100. I'll have console.log AVL root. Okay, just to see that everything's working. Node.js self. I should probably rename this then. Let me rename you. This is really the AVL tree. Okay, there we go. And that means I'll have to call this U differently as well. Okay. Okay, we got our node in the root. Looks like it's working out. Okay, cool. So insert val. I need to do const new node equals new node with a val. Val spelled properly. And then we have a base case of like if this dot root is not defined, then we simply say, okay, this dot root equals new node. This dot length, I'm going to increment u by 1, and then I'm going to I just return because I'm done doing anything to insert at this point. Okay, so this is when no root. Otherwise, find parent. So find parent and insert accordingly. So this will be imbalanced, potentially imbalanced. Let me do a let cur equals this dot root. say while cur dot. Yeah, I think I'll just use true. I can see why that would be messy for me. But basically, cur dot val is less than. I should do it the first way. Okay, val is less than cur dot val. Then we need to look at the left-hand side. So if cur dot left. Okay, this is all making sense by the way. I have to drill this into my head. So if you have a left, then we need to set cur equals cur dot left and start the whole process again, looking through that. Else cur dot left equals my new node, and I'm done. I could just break at that point. Okay, and if val is greater than the current value, then I need to check out the right side. So this is my else statement. So if cur dot right, if there is a right, if there isn't a right, then cur dot right equals my new node, and I'm done. Otherwise, cur equals cur dot right. 50 and 1 and 34 and 76 and 99, and see what that looks like. Actually, this is dot insert, and that should be it. And then I go up here, and I have a bunch of stuff now. So first value is 100. So because of the way this implementation works, it doesn't care about balance right now. It's just like inserting them in the right logical way, but it could very well be very unbalanced. Okay, one thing that they mentioned was the height. So I need to actually know what the height of things are. So this is my get height of node. Get height, and then get balance factor. So let's actually implement these on the nodes themselves and not the tree. So get height. All right. So get height. I would say math.max of get height dot left dot get height. The same thing on the right. I mean, to be honest, like you're just saving yourself like some parentheses, like whatever. Let's do it. Right. Okay. So this +1, and this is the base case of if this dot left, if there's no this dot left, and no this dot right, which is the leaf condition, then return 0. Okay, so let me just break this down then a little bit more. So const, this is going to be left height, and this is going to be right height. Except I'm going to take into consideration whether left and right exist. So this dot right, if you do, give you the height, else give you 0. Or max of left height and right height. Okay. Node. I don't need node because I am myself. If this dot, oh my goodness, if this dot left, how do I make that up? And also it didn't give me an error there, so that's interesting. We have a 4. So is this 4? Is it really 4? Did I mean a 0 here? Let's find out. It's a 3. Okay, so that did change it by 1, as expected. Here we have 25, 35, 40, 45. Okay, so I'm going to try these values instead. This is 40, 35. Oh wait, they don't think they add the same, or they do. Yeah, they should. 60, 50, and this is 45. That's a height of 3, right? 1, 2, 3. That's the max height of the thing. Yes. Okay, so that works perfectly. The balance factor is the difference between the left and the right. Okay. So if positive, left is larger. So we need to do, so the few things we have to do. We gotta figure out, so rebalance here. This will recursively check. I'm gonna do depth first search, and rebalance, recheck, so check for balance factor, and rotate accordingly. Okay. I'm gonna do that first here. Oh, okay. Whoa. Okay. So when I do my rebalance, I need to do my rotation. So I also have to put the rotate in here. So these are my like rotations. I like to make a little artwork here. Okay. Bam. Rotations. Ah. Okay. Left rotation. Right rotation. Should I do that counterclockwise? I like it. I prefer it clockwise because it's very clear what you're doing on the node itself. You're like, so here, if 2 is the 1, counterclockwise is literally me turning it to the left. It is going to the left, but it's like counterclockwise left. It's rotational. It's not left. Anyway, maybe I'm just being really nitpicky about the naming, but it's really more explicit for me. So straight, fix all left, if all left counterclockwise. Actually, all left clockwise. Then you want all right counterclockwise. Okay, so I know that the naming is probably atrocious. This is really just to help me remember. So, okay, we are back. I have to keep my voice down because there are people sleeping around me. It looks like with their implementation, they have a reference. Each node has a reference to its parent. That's interesting. I mean, that would definitely that would allow me to have the power of not having to do this funky referencing. So I think, you know what? Maybe that's what I should do here. So this dot parent. So this is like a bidirectional tree then. I think I'm okay with that. It's fine. So parent here. Parent equals parent. Okay. So what changes? Well, when I insert a value, then I need to have the node here. I don't know. This feels weird. I don't like this. So for the root node, there is no parent. Sure. For this situation, cur.left equals new node. I would say, hey, new node. Set parent to cur. And same thing for this one. That way there's a reference to the parent. I'm not sure if I like that idea because it's like this circular referencing thing. I think in JavaScript that is okay. Let me double check. Yeah, it's okay. It has a circular. It allows you to have circular referencing, so that's pretty cool. So I kind of like this idea of swap parent-child. So that is another method here. Swap parent-child. Spending too much time just not thinking, not just coding thing. Counterclockwise on a node, right? So const parent equals node dot parent. This is the grandparent. Okay. Okay, that's the. I'm gonna look up here. So this is the grandparent, the 1 basically. So you have the grandparent reference, and then you have the current. This is gonna be the new left child. So 3 is the new parent. New parent. Node dot right, I mean. So I'm to the right of this node. Then you just do this swaparoo. Choose parent. Okay, swap parents. And so that's what that helper function does. Okay. Swap parent child, that's what this is doing. It's basically ensuring that you get the nodes correct. Very good. So this is going to be something like this dot. Swap parent child. You need the old child, you need the new child, and you need the grandparent. So it's really clear what's going on. So grandparent left equals old child. If yes, then left, else right. Then you could just set the grandparent side equals the new child. New child. Set parent. You are the grandparent now. I think this is fine. So I'm gonna go with this. So swap the child parent. Swap parent child. Wait, I should mess something up. New parent. Yeah, you don't get that. Old child. What is old child? Old child is node. New child is no, this is I'm messing myself up here. So all I've done here is I've taken this 3, put it here, and then the 2 is you need to be placed on the right side. Oh, sorry, the left side of 3. New parent dot left equals node, and the node dot set parent is now equal to new parent. Node dot right. That's a good point. The node's right is now empty, so I have to anticipate that. Interesting. I'm actually seeing some patterns I might be able to abstract. I assume everything that is the left is, or the right, the clockwise is like the opposite, right? Okay, before I abstract, let me just make sure the darn thing works. Okay, so I should be able to do clockwise. So let me see this. So AVL counterclockwise on what node? Oh, actually not node, value. I think I might need to find the node. Ooh, yeah, that's fine. Let's do this instead. 1, 2, 3, 4. A little easier on myself. Two, 3, 4. And you should clockwise that. Okay. Let's see what you do. Okay. the immediate right node has, okay, is the value 3, which it should be. So this value should be 3 now, which it is. It should have a left of 2, right of 4, parent of 1. Now, the left node's parent should be 3. So I need to kind of check the parents. 4 shouldn't be touched. The right is circular, which means that one parent node, yeah, that's circular because it's the same thing. Actually, I'm verifying it here because it says circular. That means that is referring to the third node. So these parents are correct. It worked. Haha. So one thing I want to do then is kind of abstract this. I think this is like a rotation thing. It's like a main rotation. So like this is like rotate. Crap. Okay. So this, I need a node. I will need a direction. I should just say clockwise. Okay. Side 1. Clockwise. As long as it's clockwise question mark. If it's true, then the side is left, else right. And instead of this, we just say side 1. And here's be side 2. It's just going to be the opposite. I'm sure there's probably an easier way of doing that, but for now, I will just use that. So, what did I just do? So that's the right. This is the right, so this is the side 2. And this is side 1. And I think that should do it. Let's see what that looks like. So this should give me the same results. Actually, yeah, this defaulted to false. Alright. Looks like the same result. Okay. I think if I just reverse these, actually. Let me see what this gives me. Should give me a similar structure to the opposite, where I have 4 first. On the left I have 3, on the left of that I have 2, on the left of that I have 1. So here I would say left. So that should be the 3. So 3, 2, 1, right? Okay, with the parent 4. Alright, and if I rotate that sucker left, and I rotate with the true, spelled right, flag, then it should do the reversal going clockwise. Okay, the parent is 4, so that makes sense. Parent is 4, 2, 1, 3. Oh, actually I have this, yeah, okay. So parent is 2, 1 on the left, 3 on the right. And circular references. So yeah, so the abstraction of the more generalized method is better. So I no longer need both of these. I could just have one method, and it does both. All right counterclockwise. So that's where you have to like rotate the. Oh, I see why they were. Okay. This swap parent-child didn't make sense before because it had this method where if you didn't have a parent, if you didn't have this, it just did something else. But I see now why I think. New child parent equals null. So that's the situation where you have like this broken part here. So you do a left rotation on 1 and a right rotation on the 3. I'm sure I can make it more general, but that's fine. Node dot left. You want to do your rotation on it, right? What kind of rotation? You want it to rotate counterclockwise. And then you rotate right on the 3. I'll just say all straighten right. Is that how you spell straighten? Straighten right equals false. Because I want to straighten the left first. So this is the opposite of straighten right, and this is just straighten right. And the side is depending. So if straighten right is true, you want right, else left. And this, I think, should work. Straighten rotate. Okay, cool. So I turned 4 methods into 2 methods, if it works. And this should be one of those, colon. Okay, cool. Look at the left, which is the 3, and everything else is the same. So I want to instead rotate on the left here. And I have to keep that in mind that it will not rotate when the parent is a root. Okay, but anyway. So look here, we have the 2 at the head of it. So 2 should be, 2 should be here. 1 on the left, 3 on the right. Circular parents referring to the 2, and the parent itself is the 4. That's fine. So the rotation works. Excellent. I have 3 methods. Used to be 5, now it's 3. We have 1 method, which is like a helper method to just kind of handle swapping the parent out with its grandparent, because that will swap. And I have to really make note that whenever I do this, I can't touch the root, because it won't be able to do this, because there is no parent for this. Okay, so balance, rebalance. I'll just call it balance. Balance on a node, okay? Call it root by default, so it's the base. Okay, so actually this is not the recursive call, this is just it just has the functionality to do the balancing, but it doesn't actually get called recursively, not yet. If node.balance factor is greater than 0, it means it's positive, that means the left side imbalanced. Else right side imbalanced. Because it has to be one, more than one off, so that means else if. Because that's a very particular situation. Because you may not need to even balance the node if these things aren't met. So that's important. -1. If node.left.get balance factor is now, in that case, then we can talk about 0 or not, because it's we already know that there's an imbalance in the main node. This dot rotate with a true flag. This is node.left. The node, because that's the left side that's invalid. If the balance factor is exactly 0, you don't need to do anything because it's an empty node. It's like an end node, so you don't need to rotate anything at that point. Okay, I'm gonna follow the logic, but I'm a little fuzzy on why that is then. So if dot left get down. Oh, this is also like one other thing. Like there's some kind of like bad code here. Like this should be a. I don't want to have to keep calling this, so I'll just call it once. Left balance with that, and then be done with it there, and then node balance. That's what I refer to it, so I don't keep calling the same thing. And this is going to be straighten, rotate. So you need to go left first, which means it's good as is. And I'm just going to copy this for the next one. This is the right balance. I think that should do it. I'm going to do this balance upstream thing, though. And I like the name, so it looks fine. Balance upstream, node. All cur. So we call balance on cur. This balance, sorry. On cur. And then cur equals cur.parent. When do you call balance upstream? When you do your insert, which is over here, at the very end, balance. And you balance upstream on the new node. I'm pretty sure we're gonna run into an error here, of course. Of null, can't get height of null because you are working on the root, right? So I think I'll do like get left. This out left. Get height or 0. I'll put that in parentheses so it's really clear. Same thing for this dot right. Okay, try me now. Okay, because node.parent is null because you are referring to the root. This is what I was talking about. So if node grandparent, then return new child. Set parent here. So this is literally, I'm going to set parent again to null. This is when root found and root used, because root has no grandparent, and then you just return. Okay, so this is the problem. Like this dot root needs to change, and it hasn't. The reference to rooting hasn't changed. I think I changed it in rotate when grandparent. If grandparent equals null, I need to swap it out, and I swap in the new parent. If so I say if node equals this dot root, then this dot root equals new parent. So you're actually rotating on root. So let's look at a little bit more of a complex situation. Okay, 1 through 8, and it should balance such that the 4 and 5 should be the root, and everything else should be more or less the same. Set parent. Okay, so I was making a number of mistakes. I had this wrong. So this logic here, I was supposed to put a less than sign, and it had it as greater than before, so it was kind of messing up what was rotating properly. So that was the first thing. So this is the correct implementation. If the right balance is less than 0, then we want to rotate it left first, or we want to rotate the child left first, and then if it's greater than 0, we want to rotate the child right first, and then it will rotate the whole thing the other way, I believe. Yeah. Other mistake I was making was with the height. So I was mistakenly returning 0 when at the leaf it should return 1 because I was undervaluing the leaf. Sorry, I'm going to try and find it here. Here. I thought I'd be in this situation where it's like 1, 2, 3, 4 in a straight line. It should never get there. By the time you add the third one, it should rebalance to have 2 in the center as the root, and then 1 on the left, 2 and 3 on the right. So this scenario is unrealistic, which is why I wasn't thinking about it, because I saw it there. I thought that was a valid thing, but it's not. So what I did here is I have a 1, 2, 3, and I'm just going to look at the root and to show you what that looks like. So by the time you add the third one, this scenario is already out of balance because it has 1, 2 edges. And again, that's because I wasn't counting the leaf properly. So before it was getting to 4, so I didn't think anything was wrong. But yeah, here the root is 2, left is 1, right is 3. And that is the proper implementation. So when we add a 4, and in fact, let's add a bunch more. 5, 6, 7, 8. It should be properly balanced at that point. And here, like I mentioned before, it has a 4 as the center. It could be 4 or 5, depending on your preference, but I generally choose the left side first, that's all. But it will balance out. So that is my implementation here. I think the trickiest parts were definitely this balance logic. It's something I still kind of need to like dig into a little bit. Abstracting the rotations was actually, I feel, a good idea. I thought I'd have more difficulty like understanding implementing it, just because it gets kind of messy when you know the more abstraction you have, the harder it is to conceptualize what's going on. So having a little roadmap, a little blueprint of what this looked like was really helpful. But I think I don't know, if I had to do this again, I think I might just keep them separate, to be honest. It was like I wasn't saving that much time just having one here. One thing I will say, I do love the idea of inheriting from the regular binary tree, and then just adding this like balance upstream as well as all the rotation logic. This was something that tripped me up. I saw the logic in the example code. Where are you? So apparent here. So this was in the code, and I really, when I first saw it, I'm like, that doesn't make sense. Why add that? It would have been nice if this person explicitly wrote out no parent because we're at the root. This is the reason why we're using that one. That would have been helpful. What they didn't show, which I thought was interesting, was, or rather they didn't show, was this, that when you rotate the root, that you need to like really you need to say, hey, you need to set the new root to a new parent. Oh, actually, they do have it in here. It's just not in the example they showed, but it is in their code. Like if you remove the note, then you have to finagle your way into setting the right root. So that's okay. I'm out for tonight, and I will see you in the next video.